Quantum computing is a fascinating field that holds the promise of revolutionizing the way we process information. Unlike classical computers that rely on bits to represent information as either 0 or 1, quantum computers use quantum bits, or qubits. These qubits can exist in a state of superposition, allowing them to represent both 0 and 1 simultaneously. This unique property enables quantum computers to perform complex calculations at an exponentially faster rate than classical computers. For example, a quantum computer with just 50 qubits could theoretically perform more calculations in an instant than there are atoms in the observable universe. This mind-boggling processing power opens up a world of possibilities for solving problems that are currently intractable with classical computing methods. One of the key principles that underpin quantum computing is quantum entanglement. This phenomenon allows qubits that are entangled to be correlated in such a way that the state of one qubit instantaneously affects the state of another, regardless of the distance between them. This non-local connection is a fundamental aspect of quantum mechanics and is harnessed in quantum computing to perform operations that would be impossible with classical computers. Another important concept in quantum computing is quantum tunneling, which enables qubits to traverse energy barriers that would be insurmountable for classical bits. This property allows quantum computers to explore multiple solutions simultaneously and find the optimal answer much faster than classical algorithms. Quantum gates are the building blocks of quantum circuits, analogous to classical logic gates. These gates manipulate qubits by applying quantum operations such as rotations and entanglement, allowing for the execution of quantum algorithms. Two notable quantum algorithms are Shor's algorithm and Grover's algorithm. Shor's algorithm, for instance, has the potential to factor large numbers exponentially faster than the best-known classical algorithms, posing a significant threat to current encryption methods. Grover's algorithm, on the other hand, can search an unsorted database quadratically faster than classical algorithms, offering speedups for a wide range of search problems. The field of quantum computing is still in its infancy, with many challenges to overcome before practical quantum computers become a reality. However, the potential impact of quantum computers on fields such as cryptography, drug discovery, optimization, and artificial intelligence is immense. As researchers continue to push the boundaries of quantum technology, we are on the cusp of a new era in computing that could reshape the world as we know it. Classical computers, which have been the backbone of modern computing for decades, operate using words as the basic unit of information. These words can exist in one of two states, 0 or 1, representing the fundamental binary language of classical computing. In contrast, quantum computers leverage qubits, which can exist in a state of superposition, allowing them to represent both 0 and 1 simultaneously. This unique property of qubits enables quantum computers to perform parallel computations on a scale that is unattainable by classical computers. While classical computers process information sequentially, quantum computers can explore multiple solutions at once, leading to exponential speedups in certain computations. For example, a quantum computer with 300 qubits could theoretically process more possibilities in an instant than there are atoms in the observable universe. This immense processing power has the potential to revolutionize fields such as cryptography, optimization, and machine learning. Another key difference between classical and quantum computers is the concept of entanglement. In quantum computing, qubits can be entangled, creating a correlation between them that allows for instantaneous communication regardless of distance. This non-local connection is a fundamental aspect of quantum mechanics and enables quantum computers to perform operations that would be impossible with classical computers. Additionally, quantum computers harness the phenomenon of quantum tunneling, which allows qubits to traverse energy barriers that classical bits cannot overcome. This property enables quantum computers to efficiently search through vast amounts of data and find optimal solutions much faster than classical algorithms. The speed and efficiency gains offered by quantum computing have the potential to revolutionize industries ranging from finance to healthcare, opening up new possibilities for innovation and discovery. Quantum mechanics, the foundation of quantum computing, is a branch of physics that describes the behavior of particles at the smallest scales. One of the most intriguing principles of quantum mechanics is superposition, where particles can exist in multiple states simultaneously. This concept is fundamental to quantum computing, where qubits can represent both 0 and 1 at the same time, enabling parallel processing. Another fascinating principle is quantum entanglement, where particles become interconnected regardless of distance. This phenomenon has been demonstrated in experiments where entangled particles exhibit correlated behavior instantaneously, defying classical notions of space and time. Quantum mechanics also introduces the concept of uncertainty, as described by Heisenberg's uncertainty principle. This principle states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This inherent uncertainty at the quantum level challenges our classical intuition, but forms the basis of quantum computing's power. Interesting numbers in quantum mechanics include Planck's constant, a fundamental constant that sets the scale of quantum effects in the universe. With a value of approximately 6.626 times 10 to the power of negative 34 joule-seconds, Planck's constant governs the granularity of energy levels in quantum systems. Another intriguing number is Avogadro's number, which represents the number of particles in 1 mole of a substance. With a value of approximately 6.022 times 10 to the power of 23, Avogadro's number illustrates the vast scale of quantum interactions at the atomic and molecular level. These principles and numbers highlight the unique and counterintuitive nature of quantum mechanics, laying the groundwork for the transformative potential of quantum computing. In the realm of quantum computing, qubits are the building blocks that enable the extraordinary processing power of quantum computers. Unlike classical bits, which can only be in a state of either 0 or 1, qubits can exist in a state of superposition, representing both 0 and 1 simultaneously. This unique property allows quantum computers to perform calculations in parallel, leading to exponential speedups in certain tasks. One interesting fact about qubits is that their superposition state is fragile and can be easily disrupted by external factors such as noise and interference. Researchers are continuously working to develop error correction techniques to mitigate these challenges and improve the reliability of quantum computers. Another fascinating aspect of qubits is their ability to exhibit quantum entanglement, where the state of one qubit is correlated with the state of another, even when separated by vast distances. This non-local connection enables quantum computers to perform operations that would be impossible with classical computers. Interesting numbers in the realm of qubits include the record for the largest number of qubits in a quantum computer, which currently stands at over 100 qubits. This milestone represents a significant advancement in the field of quantum computing, bringing us closer to realizing the full potential of quantum technology. Additionally, the coherence time of qubits, which measures how long a qubit can maintain its superposition state before decohering, is a critical factor in the performance of quantum computers. Improving the coherence time of qubits is a key focus of research efforts to enhance the efficiency and reliability of quantum computing systems. Entanglement is a fascinating phenomenon in quantum mechanics, where particles become interconnected in such a way that the state of one particle is instantly correlated with the state of another, regardless of the distance between them. This non-local connection defies classical notions of space and time and has been experimentally verified through tests such as the famous Bell test experiments. One intriguing aspect of entanglement is that once particles become entangled, their states remain correlated even if they are separated by vast distances, suggesting a form of instantaneous communication that transcends traditional boundaries. Quantum tunneling is another remarkable concept in quantum mechanics that allows particles to traverse energy barriers that would be insurmountable for classical particles. This phenomenon arises from the wave-like nature of particles at the quantum level, enabling them to tunnel through barriers rather than overcoming them through classical means. Quantum tunneling plays a crucial role in various quantum phenomena, such as nuclear fusion in stars, and the operation of tunnel diodes in electronics. An interesting statistic related to entanglement is the record distance over which entanglement has been demonstrated, which currently stands at over 1,200 kilometers between two Canary Islands. This achievement showcases the robustness of entanglement over long distances and opens up possibilities for future quantum communication networks. In the realm of quantum tunneling, the success rate of tunneling events is governed by the tunneling probability, which depends on factors such as the energy barrier height and the particle's momentum. Understanding and manipulating tunneling probabilities are essential for optimizing quantum tunneling processes in various applications, from quantum computing to nanotechnology. Quantum gates are fundamental building blocks in quantum computing, analogous to classical logic gates. These gates manipulate qubits by applying quantum operations such as rotations, entanglement, and superposition. One of the most commonly used quantum gates is the Hadamard gate, which creates superposition by rotating the qubit state. Another important gate is the CNOT gate, which entangles two qubits by flipping the target qubit if the control qubit is in the state 1. Quantum circuits are composed of interconnected quantum gates that perform specific operations on qubits to execute quantum algorithms. These circuits are designed to manipulate qubits in a controlled manner to achieve desired computational outcomes. Interesting fact, quantum gates can be physically implemented using various technologies such as superconducting qubits, trapped ions, and photonic systems. Each technology offers unique advantages and challenges in realizing scalable quantum computing systems. An intriguing statistic: the largest quantum circuit ever simulated on a classical computer consisted of over 50 qubits and required immense computational resources to model the quantum interactions accurately. This simulation highlighted the complexity and computational power required to simulate quantum circuits on classical hardware. Quantum circuits play a crucial role in executing quantum algorithms, such as Shor's algorithm for factoring large numbers and Grover's algorithm for unstructured search. These algorithms leverage the power of quantum gates and circuits to solve problems exponentially faster than classical algorithms. As researchers continue to explore novel quantum gate designs and optimize quantum circuits, the potential for quantum computing to revolutionize various industries grows exponentially. Shor's algorithm and Grover's algorithm are two groundbreaking quantum algorithms that showcase the immense computational power of quantum computers. Shor's algorithm, developed by mathematician Peter Shor in 1994, is renowned for its ability to efficiently factorize large numbers, a task that is notoriously difficult for classical computers. This algorithm poses a significant threat to current encryption methods, as it can break widely used cryptographic schemes such as RSA by quickly finding the prime factors of large numbers. One interesting detail about Shor's algorithm is that its efficiency stems from leveraging the quantum properties of superposition and entanglement to perform parallel computations on qubits. By harnessing these quantum phenomena, Shor's algorithm can achieve exponential speedups compared to classical factoring algorithms. An intriguing statistic related to Shor's algorithm is the size of the number that has been successfully factorized using a quantum computer. As of now, the largest number factorized using Shor's algorithm on a quantum computer is 15, showcasing the algorithm's potential for scaling up to larger numbers in the future. Grover's algorithm, proposed by Love Grover in 1996, addresses the problem of unstructured search by finding a marked item in an unsorted database faster than classical algorithms. This algorithm offers a quadratic speedup compared to classical search algorithms, making it a valuable tool for optimization and data retrieval tasks. One interesting aspect of Grover's algorithm is its simplicity and elegance, as it achieves its speedup by iteratively applying quantum operations to amplify the probability of finding the marked item. An intriguing fact about Grover's algorithm is that it can search through a database of n items in approximately square root of n steps, demonstrating its efficiency in searching large datasets. Another fascinating statistic is the speedup factor provided by Grover's algorithm compared to classical search algorithms. For a database with 1 million items, Grover's algorithm can find the marked item in roughly 1,000 steps, whereas classical algorithms would require around 31,000 steps, highlighting the algorithm's superior search efficiency. Both Shor's algorithm and Grover's algorithm exemplify the transformative potential of quantum computing in solving complex computational problems at speeds unattainable by classical computers. As researchers continue to refine these algorithms and explore new quantum computing techniques, the impact of quantum algorithms on fields such as cryptography, optimization, and artificial intelligence is poised to revolutionize the way we approach computational challenges. Quantum computing is a rapidly evolving field with a growing number of applications across various industries. One notable application is in the field of cryptography, where quantum computers have the potential to break traditional encryption methods. For example, quantum algorithms like Shor's algorithm can factorize large numbers efficiently, posing a threat to current cryptographic systems. Another exciting application of quantum computing is in drug discovery and molecular modeling. Quantum computers can simulate complex molecular structures and interactions with high accuracy, accelerating the drug discovery process and leading to the development of new pharmaceuticals. In the realm of optimization, quantum computing offers significant advantages in solving combinatorial optimization problems. Quantum algorithms like Grover's algorithm can search unsorted databases faster than classical algorithms, providing speedups that are crucial for optimization tasks. An interesting statistic is the number of qubits required to achieve quantum advantage in various applications. For example, quantum supremacy, the point at which a quantum computer can outperform the best classical supercomputers, was demonstrated using a 53-qubit quantum processor. This milestone showcases the potential of quantum computing to surpass classical computing capabilities in specific tasks. Quantum machine learning is another emerging application area where quantum algorithms are being developed to enhance machine learning models and algorithms. Quantum computers can process and analyze large datasets more efficiently, leading to improvements in pattern recognition, optimization, and data analysis. The intersection of quantum computing and artificial intelligence holds promise for advancing the capabilities of AI systems and unlocking new possibilities in machine learning applications. One of the key challenges facing quantum computers is the issue of qubit decoherence, where qubits lose their quantum state due to interactions with the environment. Researchers are actively working on developing error correction techniques to mitigate decoherence and improve the reliability of quantum computations. Another challenge is the scalability of quantum systems, as increasing the number of qubits leads to greater complexity and resource requirements. Interesting statistic: the largest quantum computer currently in operation has over 100 qubits, highlighting the progress in scaling up quantum systems. Despite these challenges, the future potential of quantum computers is vast. Quantum computers have the potential to revolutionize fields such as materials science, finance, and climate modeling by solving complex problems at speeds unattainable by classical computers. Exciting developments in quantum hardware and algorithms are paving the way for a quantum-powered future. Quantum computing holds immense promise for transforming industries and solving complex problems at unprecedented speeds. With the largest quantum computer boasting over 100 qubits, the scalability of quantum systems is steadily advancing. Quantum algorithms like Shor's algorithm and Grover's algorithm showcase the exponential speedups achievable with quantum computing. Interesting statistic: the record distance for entanglement demonstration is over 1,200 kilometers, highlighting the robustness of quantum phenomena. Quantum computers have the potential to revolutionize cryptography, drug discovery, and optimization, with quantum machine learning on the horizon. Despite challenges like qubit decoherence, researchers are making strides in error correction techniques. The future of quantum computing is bright, with exciting developments in hardware and algorithms paving the way for a quantum-powered future.